Chemical equilibrium brings up the idea of reversible reactions. Reactions can be forward, where our reactants are going to turn into our products, but we can also reverse that reaction, and our products will turn into our reactants. Instead of writing that equation 2 times, we can combine the equations by just using a double-headed arrow. That shows that the forward and the reverse reaction occurs. Chemical equilibrium is the state where the concentrations of all reactants and products remain constant with time. Notice that it says remain constant with time, not that our amounts will be equal. Our molecules of SO2 and O2 are going to react to produce SO3, and SO3 can react to produce SO2 and O2. And so at equilibrium, we have all 3 types of molecules present. On this graph, go ahead and figure out which letter represents the reactants, which letter represents the products, and where equilibrium occurs. Go ahead and pause the video and determine that on your own. Restart when you think you have an answer. If we look at the graph, A is going down, so A should be our reactants, because reactants react and go down in concentration. Our product should be increasing over time, so C must be the products. And remember that we said equilibrium occurs when the concentrations are no longer changing. So equilibrium occurs around where the red line is. Notice my concentrations of products and reactants are staying constant. When a system is at equilibrium and it's disturbed, the system will make adjustments to restore that equilibrium. That's referred to as leChatelier's principle. So if a stress is applied to the system at dynamic equilibrium, meaning the reactants are turned into products, products turn into reactants, the system will change in a way to relieve that stress. The 3 different ways that we're going to talk about that can stress a system is increasing or decreasing concentrations of reactants or products, changing the temperature, or changing the pressure. The first way is changing the concentration of a reactant or product. If we add an aqueous or gaseous reactant or product, the reaction will shift in the direction to use the additional system up. If we remove an aqueous or gaseous reactant or product, it'll shift in the direction to make more of the substance that was removed. For example, what would happen in the equilibrium if more CO2 was added? If we're adding CO2, then it's going to want to use it up. The only way that it can use it up is if the reverse reaction takes place. Because then the CO2 and H2O will be my reactants, and they're producing carbonic acid. So it will shift left. So the reverse reaction is shifting left, because as you can see, the arrow is pointing to the left. What if we remove CO2? If we're removing CO2, then we're going to want to make more CO2. The only way we can make more CO2 is if the forward reaction takes place, breaking the carbonic acid down into carbon dioxide and water. So in that case, it would shift right. I would make more CO2 and more H2O. Let's look at another example together. Here we have 2 nitrogen monoxides reacting with oxygen gas to produce 2 nitrogen dioxides. So if we remove NO, then it's going to want to shift to the left to make more NO up. Remember, it shifts in the direction to make more of the substance removed. If oxygen is added to the system, then the reaction should shift to the right to use that oxygen up. And the last one, what would happen in equilibrium if NO2 is injected in the system? So if it's injected into the system, then that means I'm adding it. So I've added a product, which means it's going to shift to the left to use that product up. Another way that equilibrium is affected is if we change the temperature. Increasing temperature increases the energy. Therefore, it's going to cause equilibrium to shift in the direction that consumes that energy. Decreasing the temperature removes energy. Therefore, it's going to cause the equilibrium to shift in the direction that produces more energy. So given the equation and a delta H, remember from our last unit that delta H is the heat of reaction or enthalpy, we first have to figure out, is energy a reactant or a product? Negative 35 kilojoules, you should recall, is an exothermic reaction. If it's exothermic, make sure that you're putting energy as a product. Now, we can answer the questions of what would happen in equilibrium if more heat is added. If heat is added, then I'm adding a product. I'm going to want to use that product up, so it's going to shift to the left. Same thing, if temperature is decreased, then I'm removing energy. And if I'm removing energy, then I'm going to want to make more energy. And the only way I can make more energy is if it shifts to the right. So increasing and decreasing temperature is just like adding a reactant or a product. The only difference is you have to know where energy is by looking at the delta H if they do not put energy in the equation. Go ahead and try these on your own. Restart when you have an answer. First thing you should have done was decided if the reaction is endo or exo. It was endothermic, so we should have put energy as a reactant. When removing chlorine, it should have shifted to the right to make more chlorine up. Since temperature is being decreased, that's like removing a reactant, so it's going to shift to left to make that temperature increase again. PCl3 is added. Since I'm adding a product, it's going to want to use that product up, and the only way it can do so is by shifting left. The final way that we can affect equilibrium is changing the pressure. When changing the pressure, we'll also change the volume if it's not in a constant volume container. So a change in pressure only affects gaseous equilibrium, which means if we have unequal number of moles of gaseous reactants and products. If you increase the pressure of the reaction, it's going to shift in the direction that has less moles of gas. Because if you increase the pressure, then that's the same thing as decreasing the volume. If we have a smaller volume, we're going to want less gas to fill that container so the pressure can go back to the way it was. If we decrease pressure, then the reaction will shift in the direction that has more moles of gas. Because a decrease in pressure is a bigger volume, and so we would want more moles of gas to fill that volume to make the pressure go back to the way it was. So in A, it says pressure is increased. Anytime it's talking pressure or volume, the first thing you should eliminate are all solids, liquids, or aqueous. So pressure is increased. We have 3 moles of gas, and we have 4 moles of gas. Since pressure is increased, that means my volume is decreased, and so I want less gas. So pressure and gas are inversely related. Volume and gas are directly proportional. So which side has less gas? So it's going to shift left towards less gas. If volume is increased, that's the same thing as my pressure being decreased, and so I want more gas. So it would shift towards 4 or to the right. I'm going to try these on your own. Restart when you have an answer. Pressure is increased, which means volume is decreased. We want less gas. We have 1 mole of gas to 2 moles of gas. So it's going to shift left towards less gas. When we add chlorine, it would shift left to use that chlorine up. If we remove PCl5 or PCl3, then it's going to shift right to make more PCl3. Volume is increased, which means pressure is decreased. We want more gas. So it would shift right towards more gas. In this problem, they gave us heat as a reactant, so we know the reaction is endothermic. Since I'm removing heat, I'm going to want to increase energy by shifting to the left to make that energy back up. And finally, if we add PCl5, it's going to want to use that PCl5 by shifting right. I'm going to pause the video and try this set on your own. Restart when you have an answer. Pressure is decreased, which means volume is increased. So we want more gas. All we have is gases. We have 4 moles of gas to 2 moles. So it's going to shift left towards more gas. Hydrogen is removed. If I'm removing a reactant, it's going to shift left to make that reactant back up. Adding NH3 is adding a product. It's going to want to use that product up by shifting left, where the reverse reaction will occur. Temperature is increased. Just like the last problem, energy was given to me in the problem. It's a product, which makes it exothermic. Since temperature is being increased, I'm going to want to use that energy up, which will shift it to the left. Container size is doubled, so volume increased, which means pressure decreased, and I want more gas. And if I want more gas, then just like A, it's going to shift left towards more gas. And finally, if I add nitrogen, that's adding a reactant, so it's going to shift right to use that reactant up. Finally, look at the graph below and determine what occurred to disturb equilibrium at each segment below. So at T1, T2, and T3. At T1, notice that you have a sharp rise in nitrogen. Hydrogen started decreasing slowly, and NH3 started increasing. So that sharp rise tells me that nitrogen was added. If nitrogen is added, then we would expect the reaction to shift right. My H2 would start going down because I would start using it. My NH3 would start going up. NH3 is going up, hydrogen is going down, and notice the nitrogen is also going down after that initial increase. At time 2, we have a sharp increase of all 3 substances. So that means all 3 substances were added. So all 3 were added. We can see which way the reaction shifted, though, because our nitrogen is going down after the initial increase. NH3 is going up, and hydrogen is going down. So that means that it must have shifted right. So at T3, we can see our hydrogen went up, and nitrogen went up, and our NH3 went down. Therefore, the reaction must be shifting to the left. We have 4 moles of gas, and we have 2 moles of gas. It's shifting towards more gas, which means we must have increased the volume or decreased the pressure.